Before I start, I want to address some of the issues related to section 9.7b with the Lagrange remainder. I had extensive conversations with Nick Franklin about this, and we both agree that the problem sets in that are not the greatest that they could be for the majority of them, because they go to a level that requires you to use a calculator to actually calculate the bounds of the remainder. That's not good. That's not the point of it. And the point is that it's illustrating a concept, and it is just illustrating a concept. The idea that you can find a bound on the remainder. The idea that a function could be equal to a polynomial plus a remainder. And this we will know, and this we won't know, but we may be able to find a bound on it. Find what the biggest is that it could ever possibly be. And we will not be able to do that for every time. In fact, we won't be able to do it for many times. Much more clever mathematicians than I am can find better bounds on some of these than I can. And that's going to be a field of basically a historic value of knowing like how that would play out. We do know that when f of x is equal to an alternating series, we know that bound is the next term. So think about this remainder as being less than or equal to the max value of the derivative. So the max value of whatever the f of n plus 1th derivative is, evaluated at some z, where z is between, it's contained within x to c, so it's somewhere in there, over n plus 1 factorial times an x minus c raised to the n plus 1. So what we're getting at is that this is like the next term. This is basically the next term. Oops. But it's trying to get the biggest that the next term could ever be. That's why we do this max value thing. This is sort of like a biggest, or better yet, a bound. So I don't want you to overthink it, and over the next couple of days, we're going to be practicing the kinds of problems that you can expect there to be with that. But it is essential that you know it, and it is tested. The AP exam is all about testing concepts, and that's a concept they love to go back to. Okay, this is the last section. We're going to split this up into several days. But this one is still crucial. This is the big bad Taylor series. So bear with us as we kind of go through what this is doing. You need to know that a Taylor series is a type of power series. It's a type of power series for infinitely differentiable functions. Infinitely differentiable functions, things that you can take a derivative of an infinite number of times. So a basic power series, is of the form the sum from n equals 1 to infinity of a sub n times x minus c to the nth power, which would then give you, n equals 0 to infinity, which would then give you a sub 0 plus a sub 1 times x minus c plus a sub 2 times x minus c to the second, and so on. For a Taylor series, these a sub zeros now get very specific values. They get values related to the derivative. So a sub 0 is the function value at c, and a sub 1 is the first derivative at c over 1 factorial. Technically, this is over 0 factorial. The a sub 2 is the second derivative at c over 2 factorial, and so on. So that's the distinction between the two of them. And I didn't do a good enough job in previous years of talking about the distinctions between a general power series and a specific Taylor series. Remember that a Taylor series is centered around c, and a MacLaurin series is centered around 0. We use those same names. We have polynomials, but now the series is going to apply to infinite ones. So let's kind of look at some examples of how this is going to play out, because I think that's going to be really what you want to see. So the directions are going to be to find a Taylor or MacLaurin series for f of x is equal to the sine of x. We're going to center that at 0 because that's a MacLaurin series. And then we're also going to find the interval of convergence. Basically, now for what region is this good for? So kind of like we did with power series. So think about, we built Taylor polynomials. So you knew what a Taylor polynomial is and how to build it. Then we talked about what a power series is, which is a series that we can build and it converges around a particular area. Now we're going to build Taylor series. They're like polynomials, but they're infinite, and we're going to see how they can play out and where they converge. So much like an infinite power series can converge, an infinite Taylor series can also converge. So to build it with the sine of x, I'm going to create a table that I'm going to just do the nth derivative. Then I'm going to have the nth derivative of x. So we're just going to do, well, let's not call it nth derivative, let's call it n. And then I'm going to create a function for the nth derivative at x, and then we're going to evaluate that at c. This is going to be a table that I use for a lot of different ones of these. So here we go. The nth derivative, well, the 0th derivative is just the function, so that is sine of x. We're centering at 0, so the sine of 0 is 0. Then the first derivative, cosine of x. The first derivative of the cosine, so the cosine of 0 is 1. The second derivative, and that would be 0. The third derivative, and that would be negative 1. And we could keep that going if we wanted to. So now we define the function. The function is equal to f of c plus f prime of c over 1 factorial. Technically, this is over 0 factorial. Remember, 0 factorial is 1 if you're confused about that, and we'll prove that later when I'm not trying to run through a lot of time. But this is then times x minus c to the first power plus f double prime of c over 2 factorial, x minus, oops, not 2, x minus c to the second, and so on. Okay, now I'm going to kind of replace, this is what a Taylor series is, so we're going to now translate this to a MacLaurin, where c is equal to 0, because that's what the directions said, which means this grid's greatly simplified. F of x is equal to f of c is f of 0. F of 0 is 0. 0 over 0 factorial is 0. F prime of c is 1. 1 over 1 factorial is 1. X minus c is x minus 0, so I get x to the first. Plus, the second derivative is, well, the value is 0, so that just becomes 0. Plus, I should do one more here just to kind of clarify this out. So we got the third derivative at c over 3 factorial and x minus c to the third. So this is going to be plus, the third derivative would be negative 1, so I have negative 1 over 3 factorial x cubed. I think you can start to pattern now. Skip 0, and then we're going to be adding 1 over 5 factorial x to the 5th. Skip 0, we're going to be subtracting negative 1 over 7 factorial x to the 7th, and so on. This is going to be equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So we get that f of x is equal to the sum from n equals 0 to infinity of, we want the first term to be, well, let's see, negative 1 to the n. I want this to be, the first term to be 1, so, and then alternate afterwards odds. So this is going to be x to the 2n plus 1 is going to give me the pattern of 1, 3, 5, 7, etc. Over, then I need this to be the same 2n plus 1 factorial. So this is a MacLaurin series for sine of x. That's how we've generated that series. Now, we need to figure out where it's good. So I'm going to be just going to put the direction or thing, we're good. We're going to use a ratio test like we did before with power series. And I'm going to do the limit as n approaches infinity of, it's an absolute value, so I get to drop the -1, and I get x to the 2, I'm going to plug in n plus 1 over 2, plug in n plus 1 factorial times the reciprocal of the regular one, so 2n plus 1 factorial over x to the 2n plus 1. And I get a limit as n approaches infinity of, I'm going to carefully multiply this out, so this gives me a 2n plus 1 plus 2 is 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over 2n plus x to the 2n plus 1. Okay, when we divide with the same base, we subtract the exponents. This gives me an x squared over 2n plus 3, 2n plus 2, 2n plus 1. I'm going to get as term 2n plus 3 and a 2n plus 2. And this limit is 0 because the denominator increases exponentially. So, or not exponentially, increases a lot. 0. Okay, now we have to interpret ratio test. So this means that eventually the terms are going to 0. And 0 is definitely less than 1. And since 0 is less than 1, the radius of convergence is infinite. And the interval would be negative infinity to infinity. I need you to kind of grasp at what this means, because this is really, really neat. This means the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial is equal to the sine of x for every single value of x. You found another way to express the sine of x. So that is pretty neat, and that is a sequence that you need to know. Like, this is one that I want you to memorize. And you don't necessarily need to memorize the sigma so as much as you have to memorize that it's the odd ones. Sine does the 1, 3, 5, 7. So we're going to do, as you might imagine, exactly the same thing for cosine now. G of x is equal to the cosine of x. I'm going to do my table of n, the nth derivative of x, or the nth derivative of x, and then the nth derivative evaluated at 0, because that's my c value. So same thing, MacLaurin series. Where is it good for? Cosine. Okay, 0. This is just the cosine of x, and the cosine of 0 is 1. 1, this gives me the negative sine of x, and the cosine is 0. 2, this is the negative cosine of x, and the cosine is -1. And 3, get the sine of x, which is 0. Keep going. We're going to do 4, cosine of x, and I get 1. That's enough. G of x is equal to the, let's see, we do the first one, which is this. So I get 1 plus, we skip the next one because that's 0, and we skip this one, so I have 1 plus a -1 over 2 factorial x squared minus, sorry, no, it's not minus, it's plus 1 over 4 factorial x to the 4th. And that gets me the same kind of pattern going. I mean, well, we can put one more term down. I think you see how this goes. -1 over 6 factorial x to the 6th, and so on. So this means that g of x is equal to 1 minus 1 over 2 factorial x to the 2nd plus, and let's write it a little bit better. Let's write it as x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, or g of x is equal to the sum from n equals 0 to infinity of x to the, okay, I want this, or sorry, negative 1 to the, I want it to start with a positive, so negative 1 to the n. Then this would just be even numbers, so x to the 2n, you can check that by plugging 0 in, over 2n factorial. If I do a ratio test on this, I'm going to get that the limit as n approaches infinity of x to the 2n plus 1, so that 2 times n plus 1 is going to be 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. And I get something very similar. I get x squared over 2n plus 2 times 2n plus 1, and that is also infinity. Or, yeah, sorry, that's 0, my bad, which 0 is less than 1, therefore the interval of convergence is negative infinity to infinity, which means that the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial is equal to the cosine of x for all x. You need to know sine, you need to know cosine. They have very distinctive patterns. Sine is odd. What you need to remember is that sine is an odd function, cosine is an even function. So cosine is going to have all even powers because, remember, sine is an odd function means that the sine of negative x is equal to the negative sine of x. Therefore, odd powers. The cosine of negative x is equal to the cosine of x. Therefore, even powers. I always remember that, and I'm totally lying to you because I just realized that right now. Yay, 4th year of teaching this and I'm making some connections about even odd versus like how I'm going to remember the powers. So how do I remember? I'm going to remember that they always start with a positive, that this cosine 1 starts with a positive 1, and the sine 1 starts with a positive x. Where are we? So they always start positive, and cosine has even powers and sine has odd powers. So thank you. You've given me my way of remembering this for all time. I owe all of you that. The next and last example we're going to build is f of x is equal to the natural log of x. And we're going to center this at x is equal to 1. So this is going to be a Taylor series. So I'm still going to build the table of nth derivative at x, and nth derivative at c. So my n, 0, 1, 2, 3, 4, 5, 6, we're going to go that far down. My derivatives, or my values, this would be the original. Then I go 1 over x, which is x to the negative 1. Then negative x to the negative 2. Then 2x to the negative 3. Negative 6x to the negative 4. 24x to the negative 5. And really, at this point, it's not quite so essential that I write them all out. So I'm just going to cheat and write negative 2 times 3 times 4 times 5x to the negative 6. And then we're going to plug 1 in, which would be 0, 1, negative 1, 2. This is actually going to be negative 3 factorial, 4 factorial, negative 5 factorial. You can see where I'm going with that. So that's easier to kind of manage when I'm writing this out. So then we get the natural log of x, which is the actual true series we're trying to find, is equal to, I want to do f of, well, I can't do this one because that's 0. So we start with f of 1. F of 1 is 1 over 1 factorial x minus 1 plus negative 1 over 2 factorial x minus 1 squared, then plus 2 over 3 factorial x minus 1 cubed, then minus 3 factorial over 4 factorial, x minus 1 to the 4th, then plus 4 factorial over 5 factorial, x minus 1 to the 5th. I think that's enough to see what's happening, because my first one is just going to be x minus 1. And I'm going to have minus 1/2 x minus 1 squared. Then plus, this is going to be 1/3 x minus 1 cubed. Minus 1/4 x minus 1 to the 4th, plus 1/5 x minus 1 to the 5th. I think you can see where this is going. This is going to be equal to the sum from n equals, I'm going to start with n equals 1, because I just have a first term like that. That's going to make my numbers easier. N equals 1. Then it's going to alternate, so my first term needs to be positive, so we'll make that an n plus 1. Then I have an x minus 1 to the n over, it's not n factorial, it's just n. That's it. Now, you can also, if you're so committed to starting with a 0, right, this is the sum from n equals 0 to infinity of negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. Doesn't matter which of them you do, just be able to write and recognize them in both ways, just depending on where you start. So I'm going to use the, let's do the ratio test. I'm going to do the ratio test on this version right here, because that's the one I kind of think is a little bit simpler. So we're going to do ratio test on that. Limit as n approaches infinity of x minus 1 to the n plus 1 over n plus 1 times n over x minus 1 to the n. And I get the limit as n approaches infinity of, I'm going to show this a little bit better than the others that I've shown, x minus 1 to the n plus 1, that's just x minus 1. And this limit right here goes to 1. So this becomes x minus 1, which then needs to have an absolute value less than 1. And for that to happen, it needs to be between negative 1 and 1, which gives me between 0 and 2. Sorry. All right, like before, we need to test our endpoints. So we're going to test 0. If I plug 0 into the original one way up there, I get this. I get negative 1 to the n plus 1. Then I have negative 1 to the n over n. And negative 1 to the n plus 1 times negative 1 to the n. There are a couple of ways to think about this. One of the ways is that no matter what, you're going to have a negative in there. If n is positive, or if n is even, then this n gets knocked out. And if n is odd, then this one gets knocked out. But you're going to have a negative 1 in there no matter what. Mathematically, you can also show that by multiplying with the same base. You add the exponents, and you get negative 1 to the 2n plus 1, which, as you can see, no matter what n value you plug in, it will always be an odd power. So this is the same as the sum from n equals 1 to infinity of negative 1 over n, which then is the same as a negative summation of 1 over n. That diverges, because that's the harmonic. So that's out. Now we're going to test the other endpoint of 2. So I get the sum from n equals 1 to infinity of negative 1 to the n plus 1. And if I plug 2 in, I get 1 to the n over n. That 1 to the n is out. That's gone. And this just gives me the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n. That is the same thing as negative 1 to the n plus 1 like this times 1 over n. So it's the harmonic, but it's alternating harmonic. And the alternating harmonic converges by ASCT. And we can prove that. We've proved that many times before. So the interval of convergence is 0 to 2 inclusive. Okay, it's worth taking a look at this on Desmos. I'm not going to do it right now, but seeing that, okay, I lied. We're going to do this just really quick. So I go y equals ln of x, and then I'm going to graph, like just kind of zoom in on this region here between x equals 0 and x equals 2. We'll make this projector mode so it's thicker. Oops. And then I'm going to make these be the same color and both be dashed lines. Okay, then I'm going to do this polynomial. We're going to do y is equal to, oh, if only I could do a couple of them, but okay, let's just do a few terms. We need to do x minus 1. Oh, I'm going to cheat. I'm just going to type g of x equals x minus 1 and then hide that. So I can just say g of x plus, then I'm going to do, kidding, that's minus g of x squared over 2 plus, probably would have been just as easy just to write out the x minus 1, but hey, over 3, then minus g of x. So I keep being distracted by way too many messages coming across. Okay, I think what you're looking at is you can see that at the point right here, it's diverging. It's kind of splitting off away from that. But it's not easy to tell by the graph that it includes 2, but it does not include 0. That's essentially what's happening, is that every time you add a term, you're kind of flip-flopping up and down between all the different ones, but you're not, or between the two, but you're not ever converging beyond x equals 2. I'll add one more term in, g of x to the 5th over 5. There, flipped up, getting closer. You can play that game all day, but it's never going to match it. Okay, things I need you to memorize. Let's kind of just sit with this here. So you've got a couple of things tasks I need you to memorize. And these things that I'm writing are very visible at the start of the review. I have like a cover sheet of things, MacLaurin series you need to know. And there are some Taylor series that you should know, but definitely the things that you need to have memorized are here. So you need to memorize that 1 over 1 minus x, which is a basic power series, is 1 plus x squared plus x cubed, or so forth. You can memorize that, or you can memorize the sigma, the sum from n equals 1 to infinity, or 0 to infinity of x to the n. And you also need to memorize that this is the interval of -1 to 1, that it's only good for that. You should memorize that 1 over 1 plus x is the same thing, but it is alternating. So you get -1 to the n, x to the n, and its interval is also -1 to 1. So those are two power series you need to know. E to the x. We didn't do this one completely, but this is really easy to do. You need to memorize that it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. That is the sum from n equals 0 to infinity of x to the n over n factorial. And that has a convergence of -infinity to infinity. I like to think of a subgroup of this, if I were to split them off and make them both alternating, that the sine of x is equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1. So the sine of x is the alternating odds, and the cosine of x is the alternating evens. X to the 2n over 2n factorial, and they both also have convergences of, or intervals of -infinity to infinity. They are subgroups in my head of e to the x. And if you really want to remember a particular relationship, remember that e to the pi I is equal to the cosine of theta plus the sine of theta times I. This is from last year, and I know it's a stretch, and I'm not expecting you to really know that, but just to remind you that this was polar coordinates with a radius of 1 and an angle of theta, and this was rectangular coordinates where you had the x and the y, but the power series above show that this relationship actually does hold true. It's the special case of where you have an angle equal to 0. You can prove these series, so that's fun. And then the final one you should know the natural log. That's equal to the sum from n equals 1 to infinity of -1 to the n plus 1, x minus 1 to the n over n. And that's from 0, not inclusive, to 2, inclusive. There are more, but that's it for now. That's all I want you to kind of really know for now. And to be very clear, the ones you absolutely need to know cold are these. And the ones that you're going to be given and allowed to use are these. Although for purposes of speeding things up, I would definitely know this one too. It's just going to make things go faster if you know that in its interval and you don't have to prove it every time. So, okay, good luck. I lied, I have a little bit more for you. I need to kind of explain where a couple of those different ones come from. Let's talk about 1 over x. These are things that you will be able to look up, but when you look them up, I want you to kind of appreciate where they come from. This comes from 1 over 1 minus 1 minus x. So it is a power series generated by doing 1 plus 1 minus x plus 1 minus x squared plus 1 minus x cubed, and so on. So its sigma is the sum from n equals 0 to infinity of 1 minus x to the n, but it is alternating, so I need to grab that, slide it over, and do a -1 to the nth power. You're going to find that that has a radius or an interval of convergence of 0 to 2 if you were to test it, but you don't have to do that. Okay, we did the natural log. We did the arctangent as an exercise and as part of the thing with power series, but just to review, that ends up giving you this one. This will also be given. I know I need to keep saying that just so you have that kind of peace of mind that this particular one will be given. You're going to be allowed to have this. You're not expected to rederive power series every time. You're not expected to memorize every little bit of it. That'd be intense, and that's not what the point is. Okay, so that's arctangent. Your book walks you through and has arcsine as one that you're allowed to use. So x plus x cubed over 2 times 3 plus x to the 5th, sorry, it's x to the 5th, over 2 times 4 times 5. Oh, it is 1 times 3 times x to the 5th, then plus 1 times 3 times 5 times x to the 7th, over 2 times 4 times 6 times 7, and so on. This is a little bit more of a difficult one, and it's a longer exercise as to where that comes from. This is its sigma. You will be given this, so don't worry about memorizing this. 2n factorial x to the 2n plus 1 over 2 to the n factorial squared times another 2n plus 1. And that is from -1 to 1. That is the series for arcsine. And then finally, you have 1 plus x to the k, which gives you the series of 1 plus kx plus k times k minus 1 x squared over 2 factorial plus k minus 1 k minus 2 x cubed over 3 factorial. And this is on -1 to 1 or close -1 to 1. And that just depends on the k value. But that's easily testable with ratio test. It's best to kind of leave that there. One final exercise I just want to do is that if you get a question like find the power series for f of x is equal to the cosine of x. Sorry, cosine of root x. We already did cosine of x. We did cosine of root x. Oops, let me fix this. F of x is equal to the cosine of root x. Then we know that the cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial from negative infinity to infinity. But I need you to see that if I want to do what the cosine of root x is, all I have to do is take this root x and substitute it in for x. So I actually get to plug it into each of those, which then gives me minus x over 2 factorial, then plus x cubed over 4 factorial, minus x to the 3rd over 6 factorial, and so forth. And I could even write that as a sigma, the sum from n equals 0 to infinity of negative 1 to the n. This would just be x to the n, not x to the 2n, over 2n factorial. And as far as a domain or an interval of convergence goes, we could go with, it goes from 0 to infinity, and that's very, very clearly because x must be greater than 0 on the cosine of root x, because it's a root x. It's a radical, so you need to have greater than or equal to 0. So that's a little bit of what's happening with this. Okay, now we're done.